hit the record. So this is our human arm, and we're looking at the force that in isolation that the bicep is going to have to do in order to keep this system in equilibrium. So when you're doing an equilibrium problem, we want to do a few things. The first thing is we want to diagram our system. So even though I drew the system, physicists are going to do something a little different. We're going to diagram the system in more of a plank item. So basically, kind of like what we did on Friday, I've got a plank here. And this is our point that we're going to rotate about. So this is the point that we're at. So we have a force due to gravity that's coming down here. And we're going to call that, or this force, R, because that's a force on my origin. Okay. We're going to have the force due to my bicep, which is going upwards. And we have our force downwards of our bowling ball. And that's our 50 Newton force. We don't know this force. So we don't know this force, and this is the force of the bicep. So we've drawn our system here. Okay. And this force is the downward force of the humerus on the ulna. So just so that we have that written. So we've done our first step and we've simplified our diagram. So that's our first step, is to do that diagram. And then we can call this a force diagram. And we now know that we have two unknowns. Our unknowns are R and our force on the bicep. We don't know those at all. And so we're going to have to utilize, so that means if I have two unknowns, I have to have two independent equations. And now I can do that. I have two conditions of equilibrium. One is that the sum of my torques have to equal 0, and that sum of my forces have to equal 0. So these are going to give us our two independent equations. So that's going to give us that. So we've got those parts here. This is going to give us our two independent equations. In this case, remember that my forces are going to give me in my X, Y, and Z directions. And in this case, we only are in the Y direction. Now, the reason I bring this up is because these two conditions of equilibrium, these can produce 6 independent equations. because remember, these are vectors. Those are vector quantities, and I can have this as a rotation around this point. I can have it as a rotation that comes out of the page. I can have it as a rotation around the X, Y, or Z axis. So I can have up to 6 independent equations for this. Now, the reason I bring this up is because some of you in this class are construction engineering students, okay? And this gets us our idea of statics. So there's a whole science called statics. And statics looks at these two conditions of equilibrium. So for my construction engineering students, and for those that are in architectural design, not architectural engineering, because your architectural design students have to take general physics. These are what you're taking your general physics for, is to get to this point where you get your two conditions of equilibrium and we can produce 6 independent equations. And that becomes very important in structures. Now, granted, for you medical types and your biology types and your veterinarian types, we're looking at plant systems or human systems or a variety of things to be able to say what's going to give us our structure and how's our structure is going to be, because basically that's what the skeleton is. The skeleton gives us a framework for our bodies to be able to work with things. And bone is cool stuff. All right. Bone is way cool stuff. In fact, I've done a number of different science articles looking at what's the force required to break a bone. And bones are really cool stuff, because if you ever look at bones, bones have a variety of different structures to them. But that's where we're coming in and we start looking at physics. Now you understand why I say I hate biology. Biology has too many variables, because a physicist is going to simplify this system into 3 spots, right? Well, we know the system is more complex than that, right? We're disregarding this whole bone right here, right? Or disregarding that. We're disregarding all of those tendons and everything else. And we're just going to make some assumptions that we're looking at the force required by the bicep to hold this system up. Okay. And that's kind of an interesting analysis that we have to deal with. But I wanted everybody to know, because I got several of you that are architectural design students. I have several of you that are in construction engineering, and those folks are all going to have to take statics. And we do a whole course just on this section right here. Do a whole course on that. So it's a really interesting part of it that we get. So we're going to go back to our diagram. So I'm going to redraw my diagram. So we've got our lecture kind of components there. So we've got our diagram. So I've got my plank, and we're disregarding the weight of the plank. I've got my 50 Newton force. I have my R force. I have my F force, my force due to the bicep. But now we also have to put in our distances, because torque is going to require distances. And so this distance between my origin point and where the force of the bicep is attached, that's going to be 0.030 meters. We're going to be in 2 significant figures throughout this. And then the force, or the distance, or the lever arm, we can think about this as a lever arm, that this one is 0.35 meters. So now I have my distances. And so now we're going to write out my equations. So I'm going to do the sum of my torques. And that's going to equal 0. And this is going to be the torque related to R. And it's going that, well, we're going to just do it somewhere. We're not going to worry about direction yet. I've got the torque related to my bicep, and I have the torque related to the bowling ball. All right. I got the torque related to the bowling ball. Now let's look at this. The bowling ball is going to cause the lever arm to move this way. So this is the direction with our bowling ball or our weight, it's going to cause a rotation that direction, and that's going to be a negative rotation. This force would cause the ulna to rotate that direction, and that's a positive one. And this one is going to be interesting because we've set up the system that I'm at my origin. So this is going to be R times my distance. This is going to be F times my distance. And we're going to do this distance B. And this is going to be a positive value because of the direction that we're going to get. This one is a negative value, and that's the force related to my bowling ball or my weight times its distance. So my directions are coming from the rotation. Now, that being 0, because of how I set up my problem, I don't have to worry about which rotation it's going to be because it's at 0. So now I'm going to have my force due to my bicep times my 0.030 minus the weight, which was 50 newtons, times my distance there, which is 0.35 meters. And that all has to equal 0. So now I can calculate the force is going to equal 50.35 meters. And I've got Newton meters divided by meters. So I'm going to end up in newtons. So that's where everything's going to be nice. And I'm dividing by 0.030 meters. And when I plug that into the calculator, I'm going to get 583 newtons. So we can use our torque to help us out. Now we're going to, in order to find R, I've got to do the sum of the forces in the Y direction. R is going downward. FB is going upward. My weight is going downward. And that's got to equal 0. So we're going to have R is going to equal the force due to the bicep minus the weight. And so now I'm going to have my 583 newtons minus my 50 newtons is going to equal 533 newtons to be the force. And that we said was the downward force of the humerus on the ulna. So we get that lovely calculation. So let's do another one of those types. Oh, let's see. I'm going to put a vase on we're going to put a support here. And we're going to say that this distance, and I'm making up numbers, so life gets entertaining when I make up numbers. I'm going to say that that is at 0.30 meters. And this vase, we'll give a little flowers here. We're going to be a little more entertaining, give ourselves a little flowers. So we got a vase, and we're going to go ahead and give ourselves a weight. And that weight is 25 newtons. We got another block here. And that distance, we're going to do the same thing. We're going to make this aesthetically pleasing. So this is 0.30 meters. And this distance from here, we're going to do this distance between these. So the distance between these is 0.5 meters. And then we're going to do, that's 0.3 meters. That's 0.3 meters. We're going to have an object. We're going to have a sculpture here that's sort of hanging off the edge. And so this is right at the edge. And it's going to have a force of 30 newtons. And we want to know the forces of these two supports. So we're going to call this F1. And we're going to call this F2. We want to know the forces on these two supports to have this be in equilibrium. So from this distance to this distance, it's going to be 1.1 meters. So we've got those. There's two ways to approach this problem. Okay. We can choose where we want to do the torques. We can choose where we want to do the torque. So I can start here and I can say, I want to do my torque around this point, and we're going to call that point A. So this is the sum of the torques at A has to equal 0 because we're in equilibrium. So I'm going to have so that's going to be my 25 Newton force times its distance. And we're going to look at how it's going to rotate around A. This one's going to rotate that way, so it's going to be positive. And this will be 0.3 meters. My force at point A is at 0 because I set it up that way. This one is going to cause a rotation in that direction. So that one's positive. So I get my positive force 2. This is force 1. And it is going to be at 0.5 meters. And then this one is going to rotate in that direction. So it's negative. So I'm going to have that 30 newtons. And I'm measuring it away from point A. So that's my 0.5 plus 0.3 is going to give me my 0.8 meters. So now I've got, because I did my numbers here, at 25 times 0.3 is 7.5 Newton meters plus 0 plus 0.5 times F2 minus 24. So I'm going to get, and that's Newton meters. So I'm going to get 24 minus 7.5 is going to equal my 0.5 F2. And that's going to give me F2, and that was in meters, and this is in Newton meters, so the meters cancel out, so I'm all good. So the force from that support or this support up is 33 newtons. Well, now I can do it two ways to solve for force one. Because if I do the sum of my forces has to equal 0, I've got negative 25 newtons plus F1 plus F2 minus 30 newtons, but I've already figured out what F2 is. So I'm going to have minus 55 newtons plus 33 newtons is going to equal, or plus F1 has got to equal 0. So I'm going to get negative 22 newtons plus F1 equals 0. F1 is equal to 22 newtons. So I can look at all of that. We can use this for practical situations. Remember, nobody said anything about my artistic skills. So I have a truck and a trailer, and we might want to know what the force is on our point between the truck and the trailer. And we might know that the center of gravity, so the force of this, we'd say might be 1,000 newtons. And over the center of gravity, where this distance is 5 meters. And this one will say the center of gravity is over here. And this is going to be 8 meters. Well, I've made a really big truck. Let's try that again. That's 5 meters. I really want that to be like 1.5 meters. And we're going to make this, we're going to make this 2 meters. Yeah, that would have been a little weird. But this has a weight of, we're going to give it 3,500 newtons. And we want to know the force on our hitch. Okay, we want to know the force on the hitch. And we've got that set up, that we've got the force on the hitch. So we're going to arbitrarily put that force on our hitch as an upward force, because we've got to be in equilibrium. Okay, so we got to be in equilibrium. And so my sum of my torques have to equal 0. And I've got the torque related to the trailer plus the torque on the hitch. And then I've got the torque related to the truck. Well, that's going to be kind of interesting because depending on how I do my rotation, I may or may not be able to find that force. So let's do it this way. We're going to do a rotation from there. We're going to do a rotation around this point, around the trailer. So I'm going to get 0, and my trailer is going to be at 0 times my 1,000. This is going to want to cause my rotation to go that way. So that's going to be positive. This is going to want to cause my rotation to go that way. So that one's going to be negative. So this is going to be the force on my hitch at 1.5 meters. And this is the force of my trailer at 1.5 plus 2 is 3.5 meters. So the force on my hitch is going to equal 3,500 times my 3.5 divided by my 1.5. And it looks like I'm going to put a force on my hitch of 8170 rounded off newtons. So we can look at a variety of things, but we know that all of that force isn't on the hitch, right? We know that we've got forces on the tires and everything else. So we can look at reaction forces. And again, we're making some assumptions that are working with that. All right. I'm going to stop there because I don't want to confuse things with another concept. And I will take questions.
I have a question on this